Welcome all nodal centers for today's this morning section on this is CAD. I'm today taking CAD CAM and RPT technology. Okay.
I myself, Dr. Sarabjeet Singh from PEC University of Technology. My topic for today's presentation is conventional and unconventional machining of metal matrix composites. Okay, welcome all the participants. So the first slide of my presentation is what is the necessity to go for conventional or unconventional machining of metal matrix composites. Specifically here I'm interested to talk about conventional machining of metal matrix composite. As you check this slide, this slide represents the various utilization of metal matrix composites in the various sectors like in ground transportation, consumer product, industrial, aerospace, and electronic or thermal management system. When you check this slide, you came to know that the major chunk of metal matrix composites are used in ground transportation as well as in the consumer product. What is the basic requirement of a transportation industry or a consumer industry? They are looking for a effective and efficient secondary processing of material. They are not looking for a high-end machining of that material because it causes a increase in the cost of that product. What is basic requirement of my transportation industry and the consumer product is they are looking for a effective and efficient manufacturing process. Right? That's why when we are talking about the aerospace, they are not concerned about the cost of that product. In the case of aerospace, the safety of the passenger or safety of the equipment is more important as compared to the cost, right? So this slide motivate me to work in the field of non-conventional or conventional machining of, particularly conventional machining of metal matrix composites. So this is a survey made by the BCC Research, and it included from 2004 to 2013. Here you check that this blue strips as well as this red strip, which shows that that the metal matrix composites are extensively used in ground as well as in the consumer products. Right. When we are talking about the metal matrix composite, we classify the composite into with respect to their matrix as well as with respect to the reinforcement. Now here the broader classification of matrix is metal matrix is with respect to their matrix, that is aluminum based, magnesium based, titanium based, copper based, or superalloy based. Apart from this, the composites are classified with respect to their reinforcement. We call that as a primary reinforcement as well as a secondary reinforcement. So primary reinforcement mean to say when the major chunk of reinforcement is like silicon carbide, it's close to 10 to 15 or 20% of the total volume or the total weight of, it depends. And some secondary reinforcement is used such as graphite to increase the machinability or machining characteristics of that component. That's why we call that as a primary reinforcement and secondary reinforcement. And the composite made with the help of these reinforcement, we call that as a hybrid composite. So we categorize this metal matrix composites as simple composite as well as the hybrid composite. Hybrid composite consists of primary reinforcement and secondary reinforcement. The purpose of secondary reinforcement is to increase the machinability of the dwell component. The various reinforcement we used in these components are silicon carbide, aluminum oxide, boron carbide, so on. Now, when we are talking about the fabrication technique for this metal matrix composite, these fabrication techniques are completely developed. They are basically classified into two categories. One is the solid phase, and second one is the liquid phase. if you check from the diagram, it is classified into two categories: solid phase and liquid phase. In the liquid phase, we have a compo casting, stir casting, liquid metal, squeeze casting, or spray deposition process. In the solid phase, we have a power metallurgy or a diffusion bonding process. Almost close to 70 to 80% of the metal matrix composite, which are aluminum based, are made with the help of a liquid casting route. In that one, persons are using the stir casting as well as the compo casting. Now, what is compo casting? Compo casting is basically in which the casting of the metal or the molten metal as well as the silicon carbide, whatever you mix in that one, is casted in not in the liquid form, but it is casted in the mushy zone. We call that as a composite casting. For example, in the case of aluminum, its melting temperature is close to 650 degrees centigrade. We raise its temperature close to 700 degrees, then we pour silicon carbide. Then we rotate it, stop the furnaces so that we let it cool up to the temperature of 630 or 625, when it becomes a mushy zone, when the liquid is in a mushy zone. Then we pour it. We call that as a compo casting because it is in a mushy zone. It is a semi-solid form. This type of casting we call as a composite casting. So majorly close to 70 to 80% of the composites are made with the help of this liquid casting route. So this is very important. I call this as a very important slide. It's basically a comparison of various conventional and non-conventional machining process with respect to the machining of metal matrix composites. So here I made this comparison. This is one of the slides from my book. In this one, the comparison is based upon electro discharge machining. We call that as a EDM. This is a non-conventional machining process. Then electro discharge drilling. It is basically a extension of this EDM process or system concern of the EDM. Then electrochemical machining and ultrasonic machining, and all these are non-conventional machining process, and there is a comparison between non-conventional to the conventional. We call that as a conventional drilling process, right? Now, comparison is made with respect to the experimental time, with respect to the material, with respect to Burr formation, material removal rate, tool wear rate, accuracy level, and surface roughness, cutting forces and torque, thermal stresses, residual stresses, tool cost, and the power consumption. And here you came to know that when we are talking about the conventional drilling, the experimental time is very, very short. So again, recall the very second slide where we are talking about the need of hour related to the metal matrix composite, where the metal matrix composites are extensively used in the transportation as well as in the consumer product, where the time is a very important factor. You can't afford a component which we are going to machine take a time of close to 20 or 30 or 40 minutes. You require time to drill a hole with that is within a fraction of seconds, right? That is possible with the help of only with the help of a conventional machining. Any of the non-conventional machining process unable to give you the material removal rate as comparable to the conventional machining process. So Burr formation is in all the modern machining processes or non-conventional machining processes, Burr formation is minimum, but in conventional drilling, Burr formation is there. That is a very problematic area when we are talking about the machining of composite. Then material removal rate is in the conventional drilling is very fast as compared to all the processes. Now the tool wear in the case of conventional drilling, conventional machining or drilling is maximum. Why it is maximum? Because there is a direct contact of the abrasive particle with the cutting tool. So as you know, when we are talking about the silicon carbide is the second hardest substance on the earth. When it interacts with the solid carbide tool, it simply erode or wear the cutting edge of that tool, whether it is a drilling or it is a machining tool or any other tool, right? So when okay, to overcome this problem, we may go for PCT drills, diamond based bit or PCT based drill bits, but they are very expensive. They increase the overall cost of the production. Okay, we come to this point later on. Then material removal rate is very high, tool wear is maximum, then accuracy level attained with the help of conventional machining is large as compared to the, very large as compared to the other machining processes. Surface roughness is again very good as compared to all the processes. Cutting forces, okay, in the case of conventional machining processes, cutting forces are always very large, because there is a direct contact between the workpiece as well as the tool. Thermal stresses are very large, residual stresses are large. Okay, the tool cost is, again, I already said the tool cost is maximum as compared to the non-conventional machining processes. The power consumption is low. Okay, this table basically represent a comparison between the conventional as well as the non-conventional machining processes related to the metal matrix composite. Apart from this, this table gives you the scope of work in which you can focus your research area, like burr formation, how to reduce the burr formation in the drilling conventional drilling process. That may be one of your research area, right? Now, how to decrease the tool wear, that may be one of your area. So this table represent the basic characteristics of this table is it gives you the research potential in the machining of metal matrix composite with respect to non-conventional or conventional machining process. Next is when we are talking about the secondary processing of metal matrix composite. Secondary processing mean to say where we are. What is the difference between primary and secondary? I suppose you are able to recall it. The primary processing is you are going to manufacture a component, that is with the help of a casting or with the help of welding or any other manufacturing process. Secondary processing mean to say when you are actually going to machine it, or you are going to change the properties of that component or that material. We call that as a secondary processing, right? So we categorize this secondary processing into two categories: process to make shape of the product, it called as a machining, drilling, reaming, whatever the processes we call that is. Then process to alter the properties of the product, that is like heat treatment of that product, surface hardening. All these are change in the microstructure. All these are within the domain of secondary processing. So this diagram completely represent the various scope of secondary processing of metal matrix composite. Here it is within the domain of product shape, product properties. Product shape is with the help of material removal process and with the help of material deformation. And material removal processes included machining, drilling, shaping, milling, etc. And deformation processes including rolling, forging, bending, etc. And final shape of the product, and net product goes to the market for use. Now, product properties: heat treatment of the product, heat hardening, annealing, normalizing, final material property of the product, mechanical property, and change in the microstructure as per your requirement, or as per your requirement related to the tribological aspect of that material. So let's concentrate on the conventional machining of metal matrix composite. So various concern in the conventional drilling of metal matrix composite is tool wear, cutting forces, and surface roughnesses. So as the picture represent, this graph represents the various types of tool bit used, tool material used by the various researcher in the last decade. This data is up to the 2015, I suppose. And here, close to 28% of the researchers use the PCD, that is polycrystalline diamond. Then 19% of the researchers use solid carbide. 19% of the researchers use high-speed steel and coated high-speed steel. 9% uses, other uses 8%, and tungsten carbide close to 17%. No, the net result of all these tool material is, when you are talking about the high speed steel or coated high speed steel or tungsten carbide, that is straightway rejected by the researcher, because when you drill up with the help of these tools, it interact with the tool, then with the solid carbide particle or abrasive particle, the tool is immediately irradiated, wear out, and its life is in the case of drilling or in the case of machining is negligible when we are talking about the high speed steel or coated high speed steel or tungsten carbide. Okay, some uh, two lives are given by solid carbide and the polycrystalline diamond. If if I arrange all these tools in a ascending order, then PCT is at highest level, the second is at solid carbide, and the third one is tungsten carbide, and so on. So here, my research work at IIT Roorkee is concentrated only on the solid carbide drill bits, because they are less expensive as compared to the polycrystalline diamond. Their cost is close to 1/20 of the PCDs drill bits. If its cost is close to 5,000, then PCD is close to 1 lakh rupees. Okay, in the conventional drilling, the major aspect is cutting wear, sorry, tool wear. Then second is cutting forces, as there is a direct contact with the material and the cutting edges, the cutting forces are enormous in the case of conventional drilling. Okay, the surface roughness is again a major concern in the conventional drilling, because sometimes the loosely bounded silicon carbide particle, they act as a abrasive particle and eroded sorry uh, wear the whole wall surface, because they itself act as a cutting tool. Okay, during my research work, I use various type of drill point geometry to investigate uh, their quality characteristics, to investigate the various quality characteristics. Here, the quality characteristics used are thrust forces, torque, surface roughness, then tool wear, burr formation. All these are output quality characteristics used, and the input parameters are cutting speed, feed, and drill point geometry. I selected these three drill point geometry out of 7, 8 geometry available to me. The first one is a conventional drill. We call that as a twist drill, right? This one. This one. This one is a conventional drill point geometry. We call this as a Joe drill point geometry, and this is a parabolic drill point geometry, right? So these are selected on the basis of it. I performed some preliminary investigation, and I found that the thrust forces or torque generated in these type of geometries are much lesser than the other geometries. That's why I select these as a one of my process parameter for my further investigation, right? Some researcher call this Joe drill point geometry as a step drill point geometry. It consists of a primary step. This is the primary step, and this one is a secondary step, right? And the output quality characteristics here are thrust force. This is a signal generated for thrust force, signal generated for torque, and surface roughness, tool wear, and burr formation. These are the some of the output quality characteristics with respect to this investigation. So this is a schematic diagram for the experimentation work. We have a drill bit, we have a drilling dynamometer. So here the as the line diagram represent, uh, this is the dynamometer, and this is the metal matrix composite plate, and it is centrally placed on the dynamometer. And this is the drill point geometry. This is spindle, and the signal from this piezoelectric drilling dynamometer is gone to the charge amplifier, from where it is converted to the analog to digital converter, analog with the help of analog to digital converter, and converted into the signals, that is in terms of thrust force and torque with respect to time. So this figure represents the actual dynamometer. This is the metal matrix composite plate. It is centrally placed upon the dynamometer. This is a drilling dynamometer workpiece. Dynamometer software with computer. This is the drill point geometry. This is the charge amplifier, which is used to amplify the signal produced with the help of a dynamometer. So these are the signals produced for metal matrix composite. Now here, if you check these signals are erratic in nature. They have ups and downs. It shows that the interaction of drill point geometry with the abrasive particles here, right? And this is a signal for thrust force, and this is a signal for torque. So I perform a number of experiments with respect to different drill point geometry, with respect to with various cutting speed, variation in cutting speed, variation in speed, as well as variation in reinforcement size. Here, if you check that with respect to twist drill, with respect to parabolic drill, and with respect to jaw drill, I perform set of experiments on cutting speed. Cutting speed varies from 140, 224, 355, 450, and 560. And the feed varies from 0.03, 0.05, 0.08, 0.12, 0.19 millimeter per revolution. And here the variation in material is also there. It is with respect to the reinforcement size of the abrasive particle. Here the reinforcement size of the abrasive particle is 5 micron, 10 micron, and 15 micron. If you calculate all these parameters here, we have, I suppose we have 5 parameters here. One is drill punch geometry, second is cutting speed, third one is feed, and fourth one is reinforcement. We have 4 parameters, all at a level of feed is at a level of 5, speed is at a level of 5, drill point geometry is at a level of 3, and reinforcement size is at a level of 3. Right now, it gives you a combination of close to more than 100 experiments. When you are able to plot, if you simply plot those experiments, it gives you a very erratic nature of the result. You are unable to predict what is happening, right? So I place them all these experiments with respect to thrust force mapping. I make some zones. Zones mean to say where the forces are less than 150 newtons. I call that as a weak zone. Then intermediate zone 150 to 250, then 250 to 350, then 350 to 450, and 450 to 550, and above 550 newton. That is very high value of thrust forces. I categorize the thrust forces in all this domain with respect to the different feeds, as well as different feeds, cutting speed, as well as the parabolic, various type of drill point geometry. Now, when I came to know that here, under all these parameter, the twist drill point geometry, when the feed is close to 0.119 and reinforcement size is 5, 10, and 15, and the RPM is 140 to 560, all these are red in nature. Okay, all the thrust forces are greater than 550 newton. Now, with respect to the parabolic, there is a decrease, some decrease in the thrust force, and with respect to the jaw drill point geometry, there is a considerable decrease in the thrust force at the same process parameter, right? So here the thrust force is within the zone of 450 to 550 Newton. In the case of twist drill, it is more than 550. And in the case of parabolic, it is again within the range of 450 to 550, because some are red, some are black, and some are this brown, right? So from this one, I concluded that the drill point geometry has a, when you kept all the process parameter as a constant, then drill point geometry has a significant effect on the cutting forces. Though you can simply conclude it with the help of this figure here. Here, all these things are dark, and here the cutting forces are less than 450 Newton. Right? In the same way, I go for torque mapping. In the same way, I go for the surface roughness mapping. Here, the surface roughness attained is within the zone of 3 to 4, 4 to 5, or micron. All these are in microns. Then 7, 6 to 7, and more than 7. Now, again, you came to know that here the jaw drill point geometry having surface within the range of 4 to 5 as compared to 3 to 4 as compared to parabolic drill point geometry, where the surface roughness is within the zone of 5 to 6, as well as the twist drill point geometry, where the surface roughness is within the zone of 5 to 6. So, from this mapping of thrust force, torque, and reinforcement size, the following conclusions has been made by me. The feed along with drill point geometry are important parameter to consider for analysis the thrust force. The reinforcement size also has a considerable influence on thrust force. The effect of variation in cutting speed on thrust force was not evident from the thrust force mapping. Okay, all these are observation from the thrust force, torque, and uh, surface reference mapping. Similar to the thrust force feed, drill point geometry along with reinforcement size has considerable effect on torque. Again, the effect of cutting speed was not found significant from torque mapping and was considered as insignificant. From the surface roughness mapping, it was observed that all the process parameter cutting speed, feed, and drill point geometry and reinforcement size affect the surface roughness of the drilled hole wall in metal matrix composite. Now here, the one very important thing, when very important observation is here, the drill point geometry plays a very significant role when we are talking about the thrust force, when we are talking about the torque, or when we are talking about the surface roughness. So what is the here we have some idea that is qualitative idea. Qualitative idea is drilling geometry is a significant parameter. Drill point geometry is a significant parameter. Now, how to quantify it? So our aim is to quantify it. So we quantify it with the help of some statistical technique. We perform some statistical experiment within the domain of cutting speed, feed, drill point geometry, and reinforcement at level 1, 2, 3 as per the Taguchi methodology. And uh, we find out the various variation of the thrust force with respect to the reinforce speed. This is a speed. It shows that it's almost constant, and with respect to feed, it's a considerable increase in this one. And drill point geometry, there is a decrease in the thrust force, and with respect to the reinforcement size, it is first increasing then decreasing, right? This is some of the observation from. In the same way we have observations for torque, as well as observation for the surface roughness, and we quantify it and found found that in the case of thrust force, the cutting speed is insignificant. I only present here the graph of cutting this thrust force. The torque and surface roughnesses graphs are not available in this presentation. I I simply give the results. Uh, the thrust force, in the case of thrust force, cutting speed is insignificant, and the feed is 79%, drill point geometry 13%, and the contribution of reinforcement size is 7%. And with respect to torque, the cutting contribution of the torque is cutting speed is 6%, feed is 69%, drill point geometry is 15, reinforcement size is 9. Then with respect to surface roughness, cutting speed is 23, feed is 16, drill point geometry is 53, and reinforcement size is 80. Okay, all these percentages basically all these are numbers. So I try to generate some keywords for each and every output quality characteristics, that is thrust force, torque, and surface roughness. The keywords generated are drill point geometry, thrust force में 13%, torque, in the case of torque, drill point geometry is significant, that is close to 15%, surface roughness highly significant, close to 53%. So what is the meaning of this keyword? Keyword represents that the drill point geometry, that is jaw drill or the strap drill, it influences the thrust force, it influences the torque, it influences the surface roughness. You get the best result with the help of this drill point geometry. So it motivated me. What motivated me to carry out the research on particularly on this drill point geometry, that is step drill. So my second phase of experiment starts with the drill point geometry. And one more thing we observed from this one, the burr formation is minimum in the case of step drill point geometry. So up till now, what we did, we performed the inter drill point geometry. Inter drill point geometry mean to say when we are comparing the various drill point geometry. Now, in the next phase, we are going for the intra drill point geometry. Intra drill point geometry mean to say we have a single drill point geometry. We vary the various cutting characteristics of that. Cutting edges or dimensions of that drill point geometry. Okay, we call that as a intra drill point geometry investigation. And one more concept we originated from that with the help of variation in the cutting angles of this jaw drill point geometry or step drill point geometry, we are able to decrease the burr formation on the workpiece. So as I said earlier, that the comparison between the non-conventional and conventional machining processes gives you some research challenges. The research challenge in the case of conventional drilling is the burr formation. So what are the various the burr formation causes inappropriate contact angle among grunt carrying members, inappropriate seating of mating surfaces, imprecise assembly of component, additional processing cost for deburring. These are the some of the deficiencies related with the burr formation on the object or on the material in the conventional drilling of the materials or conventional drilling of the composites. So let's let's check how the burr formation take place in a simple twist drill. Now here you check that in the case of this is a simple twist drill, this is a workpiece, and this is the point angle. Okay. If you concentrate on the last portion of the material, which is still attached to the workpiece, and the no cutting take place up till now, no cutting take place. We are talking about the end toward the end of the drilling process. Here, if you enlarge this one, the drilling take place, the cutting forces are acting perpendicular to this cutting edge. Okay. Now here it is converted into the two component. One is a horizontal component, and second one is the vertical component. Horizontal component and vertical component. I call this component as a Rx, and I call this component as a Ry, and this component as a component R, which is a cutting force acting on the material. Right now, this horizontal, this vertical component, that component Ry is responsible for the thrust formation, and the horizontal component, that is component Rx, is responsible for twisting of that last flake of the burr or last flake of the material in the form of burr. Okay. Now what happened here? This component rotate this uncut portion of the material and place it somewhere here. We call this portion as a burr. Now this is given. This diagram is given by Co SL in the year 2003. This is a basic burr formation in the conventional drilling process. Now the point is how to decrease this burr formation. इसको decrease कैसे करना है? Now you are able to decrease this burr formation if you are able to decrease the horizontal component. Just check. Let me repeat this. In this twist drill. In this drill point geometry, here we are talking about the last flake of the material, uncut material, right? Now here the forces acting on the cutting forces are always acting perpendicular to the material. Here the cutting force is acting something like this. This is the cutting force component. Okay, you can resolve this component into two forces. One is horizontal and second one is vertical. The vertical component is responsible for the thrust force, and horizontal component, what happened? Horizontal component try to or rotated the uncut material, and it plays somewhere on the outer face of the workpiece. We call this as a burr formation. This is basically burr. ठीक है, कटिंग नहीं हुआ, there is no cutting, it is just horizontal component, rotated it and it plays somewhere here. Right? Now the idea is how to decrease this burr formation. इसको decrease कैसे करना है? The one very simple method is try to decrease the horizontal component. If you decrease this component, horizontal component, the burr formation can be decreased. Right? No, this again at a same process parameter. I perform some experiment related to the twist drill and related to the step drill, and I found that in the case of step drill, the thrust force is much less as compared to the twist drill, right? And as well as the burr formation is also negligible in the case of step drill. So this is basically a comparison of thrust force signal for twist drill as well as for the step drill. Okay, again the burr formation in the case of step drill. Okay, we call this as this is a primary cutting edge, and we call these are a secondary cutting edge. Now in our jaw drill, this secondary cutting edge are at some angle. Okay, again that leads to the burr formation, but the burr formation at this point is smaller as compared to the twist drill, because the cutting forces are in this jaw drill point geometry or step drill point geometry, the cutting forces are very much decreased as compared to the twist drill point geometry, right? Now, what I did instead of if you recall this previous figure. Now here the secondary cutting edge has some angle. Here I make the secondary cutting edge that is 180 degree. Instead of some angle, 125 or 130 degree, the secondary cutting edge is 180 degree. It is perpendicular, right? I call that as a cutting edge. So here, now what happened? So I make one hypothesis for this Burr formation. The Burr formation in twist drill is because of cutting forces component acting perpendicular to the drill axis. Okay, we already discussed this thing. Decrease in Burr formation may be observed with the step drill point geometry because of decrease in cutting forces as compared to conventional drill point geometry. Okay, then horizontal component of drill force becomes zero when secondary cutting point angle is 180 degree. अगर मैं इस horizontal component को zero कर दूं, if by some means I try to make this horizontal component as a zero, then I suppose that there will be no Burr formation because no bending will be there, and may cause further decrease in Burr formation or Burr free holes may be produced. Right, that is my hypothesis, and I work on basis of this hypothesis, and I make a drill point geometry. Here the variation in the process parameters are with respect to the step diameter. The step diameter is 4, 5 and 6, and the point angle is 90 degree, 118 degree and 130 degree, and the secondary cutting edge of drill point geometry is remain constant, that is 180 degree. All these are with the help of all drill bits are of a solid carbide. No, when I perform the experiment, these type of signals, step signals are generated instead of the regular signal. Okay, here, if you recall, if you check here, the progress of this drill bit is shown somewhere here. Okay, this represents the point A. At this point, the drill bit is on the surface of the material. Okay, and this is represent A to B. Please check somewhere over there. If you check this A to B, here A to B is when the primary cutting edge is completely in contact with the workpiece material. Then B to C, when the primary cutting edge perform the cutting operation on the material, and C to D represent when primary as well as secondary cutting edge both perform the cutting operation. Then D to E represent when both the primary as well as secondary cutting edge perform the drilling. Then E to F when only secondary cutting edge perform the drilling. Okay, it's E represent the point where the primary cutting edge going to leave the workpiece, and only secondary cutting E to F represent only when there is a steep decrease in the cutting forces, where only the secondary cutting edge perform the drilling. F to G, where when the only secondary cutting edge perform the drilling, then G to H there is a steep decrease in the cutting forces. Right. So this represent the flow of. You can check the flow of drill point geometry from position A to position H with respect to the various cutting edges, and all these are represented somewhere with the help of the thrust force signal. Right. So when you analyze, compare these drill point geometry results, holes made with the help of these drill point geometry, we observe that there is a no Burr formation on the exit as well as on the entrance side of the workpiece, as compared to the Burr formed on the workpiece with the help of a conventional drill point geometry. Here you check some of this is a very clean hole made with the help of twist drill, but here we have some Burr formation. Here we have some Burr formation. Okay, with the help of conventional twist drill point geometry, Burr formation is observed. With the help of this modified drill point geometry, the Burr formations is reduced to a considerable extent. Okay, some burrs may be available over there. They may be shown with the help of microscope or some other magnifying instruments. So when I investigate the chip formation, so two types of chips were observed during the drilling process. One is regular curved shape, V-shaped chips, okay, and second type of chips are formed with the help of a secondary cutting edge, that they are in a ring type of chip formation, right? So we try to make some analysis how these chips were formed with the help of this secondary cutting edge. So we investigated and came to know that at the end of the drilling process, when only the secondary cutting edge is in action, now what happened? This last flake of the material, it is constrained by the workpiece from this side, constrained by the uh, this cutting tool from this side, constrained by the cutting tool from this side. Okay, if you, this is the extended portion of this one. Okay, this is the workpiece. This is constrained from this side, and uh, vertical forces are acting on the surface. No, if you analyze this last flake of the material, it looks like a constraint ring. It looks like a constraint ring. Constraint mean to say it is constrained from these two sides, and load is uniformly distributed. Load is acting on the upper side. Okay, as there is a lot of temperature is generated, heat is generated on the surface of this one. Okay, as the base is aluminum base, the coefficient of expansion is very high. No temperature stresses are generated on the last flake of the material. Because of this temperature stresses, the stresses are acting in this direction. Please check this slide. The temperatures, these are the thermal stresses. TS represent the thermal stresses. They are acting on the material in this side, right? No, because of these thermal stresses, okay, the material is constrained, completely constrained, right? The forces are acting in this way. Right? The forces are acting in this way, it completely constrained it. That's why the Burr ring type of chip formation is there. Right? Am I able to clear my point?
So, but if you are forming such a sort of a ring, is there is a possibility that it will take off the some portion from the original metal itself, because what your intended is to make a hole. But it is not a usual gradual forces not coming, because at that time it is perpendicular. The dribble is perpendicular in the secondary area. So is there any chance that it will be just shear off that due to that force, no, you will just shear off that ring, will just shear off from the edge, and it may
there may be the chances कि shearing may take place. Shearing may take place. Shearing may take place.
May lead to an underfinished product, or that underfinished mean irreparable loss may happen.
But the thing is कि due to the temperature produced at that zone, it provides the additional stiffness and rigidity to the last flake of the material. Right? Because of the temperature stresses, the material has a tendency to expand. It has a tendency to expand, but you are not going to get it expand, because it is constrained from the workpiece side as well as from the tool side. Okay, you are not allowed to allow the material to expand. So what happened here? The stresses will be produced. And it provides the additional stiffness as well as the rigidity to the last flake of the material. and that additional stiffness and rigidity is beneficial for us. It's beneficial. Why it is beneficial? Because
That piece only will be there.
that piece will be removed from the
Because
material.
it will be made as an metal piece.
Yes. That's why we have ring type of chips formation is there. We observe the chips, then we analyze it. Why this type of chips are formed here? Then we concluded it. We go for the literature. We find out the some expansion of something related to expansion of shells, expansion of plates. We analyze these are the mechanisms, right? Then we came to know that okay, this may be happening somewhere here. Here it's like a basically it's like a hollow plate. Expansion is like a hollow plate.
Something like a hollow piece.
It's a hollow plate.
It cannot expand
Yes.
in the both directions.
Yes.
This direction, this direction.
Yes.
So it will be just. So then there will be a lot of rubbing force there, right?
There will be a lot of
a lot of rubbing force will be there in the chip, right? Because it's perpendicular, no?
yes. Rubbing.
I mean, a lot of friction will be created on that ring surface, right?
Yes.
Due to
But what happened in the case of aluminum based material, there is a increase in the temperature at the workpiece. That increase in temperature is very high. It is close to 200 or 250 degrees centigrade. Okay, that increase in temperature is also beneficial because it decreases. It basically decreases the cutting forces also.
yes.
Right.
Because it's a
So
solid
that increase in temperature is because of the primary cutting edge.
Okay.
So
That
here
increase in
here the cutting how the cutting takes place. Cutting takes place with the primary cutting edge. It heated the material. Okay. When the secondary cutting came into action, no, it has a heated material. It is going to cut a material which is already at a temperature of 200 or 250 degrees centigrade.
Yes.
Right.
Process it's a semi-molten stage.
Yes.
In case of aluminum.
Yes.
Because it's
Not semi molten.
Semi-outside,
It's not a semi molten state.
some sort of
Some sort. Okay, you may call it.
semi-solid.
But semi-solid, it started when its temperature is above the lower crystallization temperature of the material, right? But lower crystallization temperature of this aluminum is close to 450. Here, the rise in temperature is not more than 250.
So it won't create any metallurgical changes or nothing like that.
Metallurgical changes will observed when the temperature come to the critical point.
It's not coming to that.
It's not coming up to that.
So my question was that
Still we call that this here it's a cold working.
it's a cold, yeah.
It's a cold working. That I suppose it's a more appropriate and right word.
In the conventional drill, it's already a cold working process. But here it may come to the question was the method may come to that hot working process.
Yes. Definitely. Okay, these are the some SAM images generated from conventional drilling. Here you can see some of the loosely bounded SiC particles on the surface, and as you check, this is a groove formed by the SiC particle, which increases the basic surface roughness of that whole wall surface. Okay, then subsurface damage. Okay, these are the surface damages by this one. Then it's not. In the case of metal matrix composites, it's not like that. Key SiC particle always increases the surface roughness of that whole wall surface. Sometimes they act as a burnishing and they produce some burnishing and honing effect. Okay, the SiC particle they itself act as a as a cutting tool, and they may start rubbing with the whole wall surface. Sometimes they generate a groove. Sometimes they act as a burnishing, and they produce some burnishing and honing effect. It depends upon the reinforcement size of the material. Right? If the reinforcement size is very large, it's close to 50 or 60 micron, then it is going to produce a groove on the surface. If its size is very small, close to 5 or 10 micron, then it may be going to produce some burnishing or honing effect on the surface. Okay, some burnishing and honing effects were observed by the SiC particle on the surfaces. Okay, here it is surface roughness is 4.79. Here the surface roughness is 3.79. Okay, apart from this, our second motive is here I skipped some of the slides, which shows the results of effect of process parameters on the output quality characteristic. I skip all these in second phase of experiment. Now, in the third phase of experiment, we finalized some parameters related to the jaw drill point geometry. Okay, this will be the parameter of jaw drill or step drill point geometry, which we are going to investigate in the third phase of experiment. In the third phase of experiment, what we did, we developed a process which further increases the surface finish of the drilled hole wall. So basically, it is a online process. We are increasing the surface finish during the process. It's not after the drilling process operation like a abrasive flow machining. It is online drilling process, right? So here we develop a setup. We call this setup as a abrasive assisted drilling. If some burr formation is there, if still some burr formation or micro burring is at the second phase of experiment with the help of step drill geometry, with the help of this process, we are able to reduce it or minimize it. Now, what happened here? As you check this one, this is the drill point geometry. Yeah, this is the drill point geometry. This is the drill point geometry. These are the magnets. We place some magnets, and these are the SiC particles poured on the surface. Okay. During the rotation process, when the drill is rotating at certain RPM, the drill carries the abrasive particles. Now here the cutting is because of the drilling action, cutting action of the cutting edges, and these abrasive particles are entrapped in the fluid of the drill bit, and that fluid provided them a centrifugal force, and the free particles are impinges on the surface of the hole wall. Right, during the rotation process, centrifugal force is imparted, and because of this centrifugal forces, the silicon carbide particles are impinges on the whole surface, which further increases their surface finish. Apart from this, some pulling action is generated with the help of placement of some magnets. Okay, I place some magnet somewhere here. Now this magnet act as a they try to pull the magnet SiC particle toward them. Right, we magnetize this SiC particle. Okay, they try to pull the magnetic particle. Oh, okay, the various forces acting on this one is forces because of the centrifugal action. One is downward force, that is due to the gravity. Second is centrifugal force. ये नीचे भी ऐसे they are coming downward and they are rotating also, and some magnetic pull is there because of the magnetic flux, electromagnetic flux generated over here. So this process further increases the surface finish or surface roughness of the drilled hole wall surface. That is one of the setup we designed at IIT Roorkee.
Will that particles may come out through the flute?
Yes, the yes, the property of that fluid is it imparted the centrifugal force to the SSU particle. They are moving in this radial direction as well as downward direction. ऐसे भी जा रहे हैं, नीचे भी जा रहे हैं. नीचे जा रहे हैं, it's because of gravity. In this direction, it is because of the centrifugal force. So this process started after the cutting operation when hole is already drilled. We let this process go for some time or for 20 or 30 seconds, not more than that.
But then you have to redesign the flute also, right?
Huh?
You have to redesign the flute also because in the conventional drilling process, particles will climb up through that flute. In the conventional process, the chips will be climbing up through that flute, right? So if your intention is that you have to carry the whole material downwards.
These particles are basically these particles in a slurry form. It is a water-based slurry or oil-based slurry in which you have some concentration of the particle, maybe 10 to 15%. It is not a purely a particles. It's a slurry form. We just pour the slurry like a coolant.
So you are just pouring.
You're pouring it. It's pouring. Right?
But this tells me chance that this slurry may be coming up through the conventional. In the conventional drill, if you are putting some slurry or some chips to this, it will just climb up, in the conventional drilling process. Because due to the particular shape of that fruit.
Okay.
Will it happen here also?
If it is coming upward, then it is again advantageous to us because it is more interacting with the surface, whole wall surface. Because of it's just like a coolant. What I told you, it's just like a coolant. Coolant you make some additive particles, that is SiC particles in the coolant and pour it. Okay, if it is coming in upward direction, it means it has a more interaction with the whole wall surface. Then it's again advantageous to us. So it is basically, it depends on the time. It's close to 10, 20 second, 30 second, 40 second. Within that one, we are able to very good results. Although it may damage this cutting tool also. This process is not so simple. It damages the cutting tool also. Yes. Okay. Next is some unconventional machining processes for composite materials. In this one, we discuss this ultrasonic machining. These are also from some figures from my book. Here you have tool holder studies there, converter, ultrasonic transducer is there, and it is basically a mechanical process in which the abrasive particles are impinges on the surface of the material and eroded it, and you get the cavity of the surface, desired surface. Here, this tool is just replicate of the images, replicate of the workpiece you required, right? I suppose this is a very simple process, ultrasonic machining. Then we have electric discharge machining, right? Here the EDM, we call that as the EDM. I would like to concentrate more on electro discharge drilling. Okay, let's concentrate more on this. Basically, this setup is developed by one of the research scholar, that is Singh at IIT Roorkee. So he used the conventional EDM process. So he makes some arrangement, something like this. So this is You remove the conventional tool from this one. Okay, then place some motor here, and here this is the cutting tool, right? Right. So what happened here in the electro discharge drilling? The simple EDM process is there, electric discharge is there, as well as the electrode is revolving. It's rotating. Sorry, the electrode is rotating as well as discharge is produced over here. Okay, we call this as a electro discharge drilling. This is the setup available at IIT Roorkee. Okay, from this, after this, we have one more process that we developed at PEC University of Technology, that is electrochemical discharge machining process. It is basically a combination of electric discharge machining (EDM) and ECM process, electrical charge machining. And what are the properties of this EDM and ECM processes are? They are used for the conductive material, but you can use this ECDM process for the non-conductive or for the composite material, such as metal matrix as well as polymer matrix composite. आप दोनों के लिए इसको यूज कर सकते हो. So this is basically a combination of EDM as well as the ECM process, and suitable for hard and brittle electrically non-conductive material. Material removal rate due to thermal heating, melting, and chemical etching of the workpiece. Okay. So this is the schematic diagram. I will show you the real diagram of this figure. Okay. Now you just check here. This spark is generated. Here this spark is generated because of ECDM process. So this is the ECDM machine. Here the spark is generated. And here the workpiece is polymer matrix composite PMCs. Now how we make the PMCs, that is given somewhere in the slides. Okay, fabrication of hybrid PMCs, polymer matrix composites. Okay. Okay, these are the fabricated composite. Why we call this as a hybrid? Because in this one we use this glass fiber as well as the silicon carbide. We have some layers of silicon carbide, then we place some glass fiber, then we place some araldite over here, matrix epoxy is there, right? And we make a stacking of all these things and make this composite. Okay, these are the some SAM images or hole drilled, micro hole drilled by ECDM processes. These are the SAM images which shows the ECDM processes. Okay, these are the some of my papers, research publications. These are some of research publications. Thanks a lot.